Hello. Yeah. If you've ever heard from me before, you know that I like talking into microphones. So that's good. I'm glad to have one. I'm Ian. I'm working at Télécom Sud Paris with Joaquin and Michel over in Carleton in Canada. Today we're just going to give a brief presentation on quantum support vector machines for anomaly detection. So a lot of fun buzzwords in there, and they'll all come together and get along well. So briefly for this presentation, we'll go over a bit of motivation. I'll describe a simple attack, and we'll use that to talk a little bit about quantum support vector machine tomography. A lot of cool words in that, and then we'll talk about some limitations in future work. So just for a little bit of context, one of the big focuses of the thesis is on quantum cybersecurity, but just beyond cryptography. So looking at various algorithms and their potential implications for cybersecurity applications. And in this presentation, we'll specifically be looking at a little bit of graph analytics, anomaly detection, and machine learning. So that's all fun. Okay, so Ludovic mentioned this just a little earlier, but in some of my previous work, I looked at graph analytics algorithms. Specifically, we showed a pretty fast way to quantify which nodes are very important in a network for keeping two critical nodes connected. And we ended up using this in the context of security or quantum network security, where some nodes could be compromised, and we want to figure out which nodes are most important to look at. In this context, we have a little bit of a toy problem. Bob expects a certain state being sent from Alice, and Alex sends an unexpected state. So we're going to talk a little bit about an entanglement attack. And in this case, it's actually quite a simple entanglement attack. It involves replacing a pair of particles, AB, with AC. So you just take one particle, throw it away, and send in another. How do we detect this? So in a lot of normal applications for quantum computing, we can use a tool called tomography. So we take a whole bunch of samples of a quantum state. We measure it many, many, many times in a few different orientations, and eventually we can get a good idea of what that state is. And something that's very nice is we can figure out parts of the quantum state, which means if we have certain expectations for what that state is, we can find anomalies in those states. Problem is, we need many copies to do this. So are there more efficient ways to look at the features we want instead of trying to understand the whole state all at once? Well, we do have something. So let's zoom out a little bit and talk about one great method for separating something into, for example, or just any two categories. In this case, we want to separate it from, we want to separate malicious from expected states. So you might want to use something like a neural network, right? If you don't have prior information about how to separate this, or the math isn't simple. A neural network, if you are doing a binary categorization, is really just a wobbly boundary where if you're above the boundary, you're in one category, and if you're below the boundary, you're in another category. We have something else, which is very nice, called a support vector machine. And it's a lot like a neural network, except instead of a warp boundary, you warp space and then put in a flat boundary. If you're above the boundary, you're in category expected. And if you're below the boundary, you're in category malicious. And so this is all nice, but why are we talking about it? Why not just use a neural network? Well, support vector machines have one very nice property, which is that training a support vector machine is equivalent to a matrix inversion. So instead of gradient descent, which is not especially quantum friendly, we have something that quantum computers can do very well under very specific circumstances. So what is a quantum support vector machine? Well, it's something that takes advantage of the equation in your bottom right here. You don't have to understand everything going on. I suppose the main thing is nothing except omega, y, and then b and alpha really matter. Everything else you can mostly ignore. Y just represents the category of each data point. So it's a vector where you're +1 in the ith entry if you are expected, and -1 if you're a malicious state. So it's just a bunch of ones and minuses ones. The omega there tells you the distance between the I and kth data points in your warp space. So that's just a matrix that tells you the distances between everything in your new space. And then the B and alpha represent the direction of the hyperplane that you are training to separate your malicious and your expected data. So all you have to do, and this is much easier said than done, is perform this inverse matrix on your labels and you get the right thing. The nice thing about that is there's a quantum algorithm for doing inverse matrices, and that is in your top right mostly. The main idea is you just invert the eigenvalues, you get the inverse matrix, and in the case that the data is well structured, that means the eigenvalues are well behaved, and the data can be efficiently loaded in. These are two big ands, or two big ifs. If both of these can happen, you can get an exponential improvement on your matrix inversion. So, what now? Well, we want to distinguish if a state is expected or malicious. In this case, in your bottom left, the state is expected if it is something entangled. So we're dealing with an entanglement attack. And in this case, that means that we want to figure out, is the state that we got entangled or unentangled? So we have two categories, and we want to be able to separate them. Once again, bottom left, that's an example of a whole bunch of entangled states. So that's a circuit that generates entangled states. On the bottom right, we have a circuit that generates unentangled states. What we can do, because we're in quantum land, is we can represent a whole bunch of things at the same time. So the big idea is in more standard uses of quantum support vector machines, you load in a whole bunch of data with quantum RAM and you do a whole bunch of stuff. But that isn't necessarily very easy to do. We can avoid that problem by just generating all of the states we need with parameterized quantum circuits. And we have those two there. In the end, when we do this, when we make this synthetic data, which represents all of our possible states, and we train a quantum support vector machine on it, we get what you see in the top right, which is a nice confusion matrix, which tells us, okay, we're pretty good at distinguishing between entangled and unentangled, or expected and malicious states, which is great. However, we've got a few limitations we need to talk about. So there's three main limitations for quantum support vector machines. One, Usually, you need to use quantum RAM or yeah, it's called that. It isn't exactly that, but it's pretty much a way to have a whole bunch of data stored and to extract all of that data very, very rapidly. Uh, Turns out that at the scales we need for quantum support vector machines, quantum RAM might actually not be an appropriate technology. It might not be possible physically because it requires either very low error or it requires a really, really powerful coprocessor, which can probably solve the problem on its own. However, since we're using synthetic data, we get to avoid that problem. Another problem quantum support vector machines have is they need well-structured data. So the eigenvalues have to be very nice. We kind of avoid this problem. So under the right circumstances, if you pick the right circuits to make your expected distribution of states and your malicious distribution of states, you might get pleasant eigenvalues. But no promises there. In our case, we get pretty good eigenvalues, and it's not a huge problem. But now we have the final limitation, and this one hurts us, and future work is going to be needed to address it. So when we train up our quantum support vector machine, what we end up getting is, or what we want is a plane that separates our good and our bad states. But what we really get is the normal vector of that plane. So the vector pointed just away from it. And to figure out if our state that we're measuring, so we're trying to categorize something, to figure out if it's above or below the norm, we take the dot product, that normal vector, with our sample, which sounds fine until you realize that the length of the two vectors is very important. So it turns out that when you train up a quantum support vector machine with the standard description of it, you end up with sometimes very, very short normal vectors. So when you take the dot product, you actually end up getting very small numbers. And when you end up measuring very small numbers on a quantum computer, you end up in a situation where you have something like 49% chance for 0, 51% chance for 1. And you have to do a lot of measurements of exactly the same thing to distinguish, am I just above that 50% threshold or am I just below that 50% threshold? So to summarize, while we get these really nice numbers where we categorize things correctly, that's only after a lot of measurements, which, I mean, at that point, why aren't we doing quantum tomography? Well, the future work is going to try and avoid that problem. And it's a little bit of a change in topic, but it's closely related in the end, and the math is very nice. Instead of working with large data sets, synthetic or otherwise, what we can do is have an environment that we can define in with a quantum oracle, which involves, or sorry, we pretty much make the goal, given our environment, given our current state, what is a good action? This is very general. It can also be applied to anomaly detection, but a few other things. And the main point is, with this, we're going to be able to avoid the third problem. And I'll just briefly describe the idea here. And if you have more questions, you can ask me after. Pretty much, you start with a naive action classifier, which we'd represent with a support vector machine. We simulate every state in superposition. We use our classifier to figure out what the best move is in our current state, move to the next state, and we perform a few of those. we sum up the reward, and we label what the best first action was. We use all of that to train up a new support vector machine, and then we repeat the process over and over again. This ends up giving us a lot of structure and a lot of nice properties, and my future work is headed more in this direction, and we'll be able to avoid all three of those earlier problems. So that's the main stuff. If anyone's got any questions, feel free to ask. Thank you.
So I don't work in quantum, so maybe this is a silly question, but I'm wondering to what extent your anomaly detection generalizes. So you talked about detecting anomalies in quantum bit patterns, but there's anomaly detection that's done in so many other fields, like in networking, and it's used to detect DOS attacks and all kinds of things. So to what extent can anomaly detectors in the field of networking be sort of transformed to be reposed as a problem in this framework to help you? Yeah.
Yeah. So the nice thing is this is actually a very, very general approach. And the only limitations are the ones that I list here. So if you're trying to separate two kinds of data, and you can create the synthetic data with parameterized circuits, that means that you can avoid problem number one. Problem number two, you still have to solve. And problem number three, you still have to solve. If you can solve both of those problems for your given thing you're trying to classify, then you can potentially get these benefits. And my longer term goal with the reinforcement learning is to give even a little bit more structure so that if you can frame the problem as a reinforcement learning problem, you might be able to get these advantages as well. So I like generality. I'm a mathy guy on that. Thank you. Any other questions?
Yes. I didn't understand the role of synthetic data. So you create synthetic data that are labeled, right? And so if you have a model that is able to generate synthetic data with a label, it means you know already how to distinguish attacks and normal points.
Well,
so you don't need to know how to classify because you know already what are the characteristics that distinguish them.
Well, yeah, so you do know the characteristics that distinguish them, but that doesn't necessarily mean you have an easy quantum algorithm that'll spit out one in this context and zero in the other context. If you were able to measure an infinite quantity of them, maybe, but it isn't necessarily the case that you have, just because you can create all of the things from one category and all of the things from another category doesn't mean you have an easy way to distinguish the categories with a single sample. And so the goal here, if we were able to solve problem 3 at least, with the norm is you get one sample or only a few samples, and you have a hyperplane that very effectively separates your malicious and expected data. So you do need some information about it, but how to generate just the general data and how to distinguish them is like not exactly the same problem. Sometimes it can be, but not necessarily. But just to be clear, in the case of our toy problem, it's probably the case that you can come up with a clever solution.
And I guess the confusion matrix that you show is not on the synthetic data, but on the real data.
It's on the real data. Yeah.
So at the end, you can see if the synthetic data are good, thanks to the confusion matrix.
Yeah.
That certifies that what you invent works for your classification.
Yeah. Thank you.